Okay, and so what I'm going to do is I'm going to take this RLC circuit that we had from last week, and I'm just going to copy this, and I'm going to paste it over here into a brand new window. All right, and then I'm going to delete the inductor. Okay, so we're just going to talk about an RLC circuit here, and I guess I guess I need a capacitor here though. So then, but this at least gets me a starting point, so it saves me. So we're going to come over here to basic capacitor, and I'm going to choose my capacitor to be, I think I was using something like a 0.2 micro. Okay. And the resistor, I don't remember. I think I was using like a 1K here. Hold on, let me check my numbers. All right, so 0.02 and 1K. All right, so we're going to have a 1K ohm resistor and a 0.02 microfarad. So 0.02 microfarad capacitor. All right, now if this is going to be a high pass filter, then the capacitor actually needs to come first. Okay, and I'll go over that here in a minute. So, but let me redraw this. So I'm going to have the resistor there. All right, so all right, so here is our circuit. Okay, and remember that I think I can put text in here. So let me see where. All right, so if you remember at DC, all right, so at DC, a capacitor looks like an open. Okay. And at high frequencies, the capacitor acts like a short circuit. Okay. So, like I say, forgetting about the Bode plot for a minute or two, just think about this statement. Remember from the DC class, right, that the capacitor looks like an open circuit. And at high frequencies, therefore, it's the opposite. It looks like a short circuit. And what we're really looking for here as a filter is we're looking at the voltage compared to Erase text. Control Alt A. Okay. All right. So we are looking at the voltage out divided by the voltage in, okay, which gives us the resistor divided by the resistor plus J times the capacitive reactance, okay? And so this is our transfer function. A lot of times we use that term transfer function to indicate okay. So we've got the voltage out divided by the voltage in. We're looking at the ratio. How much voltage do we put in? And then if we put in this voltage, how much are we getting out? So that's the aspect of what we're trying to do here is we're feeding a signal. So again, you think about it like an antenna coming in. You want to listen to the radio or whatever. So you have a signal coming in. Okay, so we have this signal coming in from the antenna, and we want to pass it through to our amplifier, to our speaker, so we can listen to it. But the problem is that there's lots and lots of frequencies coming through there, right? There's lots of radio stations transmitting on different frequencies. So what we want to do is we want to filter out the frequencies we don't want to listen to. So we basically want to tune in that one frequency of that one radio station that we want to listen to, okay? And so that's where this voltage out over voltage in piece comes from. Now this is really just, right, this comes from the voltage divider rule, where normally we would have like the VN would be up here multiplied times the R, okay? But what we did is just effectively divide both sides by the voltage N, and that gives us this ratio. So the impedances here, we have the total impedance. It's a series circuit, so the total impedance is R plus J times the capacitive reactance, right? And then, so the voltage here, which we're then going to feed this voltage out to our amplifier and our speakers, okay? And so this gives us our ratio. Now, the question is, okay, so here's the question for you. If we come back and we look at this text up here, at a high frequency, the capacitor acts like a short. So what does that mean? What is the value of X of C at high frequencies? Anybody want to take a stab? Yeah, this is a question for you here. So what is the value of the capacitive reactance X of C at a very high frequency? Effectively zero. Exactly, Alec. So so if that's the case, you have R divided by R. What's the phase angle? Zero. Yeah. Okay. So the phase angle is zero because you just have resistance divided by resistance. There's no J, so there's no phase shift at all. Okay. So at very high frequencies, you got R divided by R, which means that you're getting out the same voltage as you're putting in. Remember, it's kind of like, I just said it over here. This is like a short circuit here. Okay, so it's like this is your circuit here. There's no capacitor. And so you're taking whatever's coming in, you're just passing it right through into your next circuit for the most part. So this is whatever this voltage in is, that's what your voltage out is. It's a gain of 1. Okay. And so if we go back then to our question, all right, for a high pass filter, okay, and that's the filter I passed because we're passing high frequencies, okay, the phase angle is 0. Okay. Now if I flipped the resistor here, okay, so if I flip the resistor and the capacitor, and I put the capacitor where the resistor is, this changes because now I get a J X of C. Okay, so X of C becomes very small at high frequencies. I'm not going to say close to 0, but there's a J here. Okay, so since and then this is very small, this becomes very small. Okay, but R is not small. R is still 1,000 ohms. Okay, so what happens is at high frequencies, here then, okay, so at high frequencies, you end up getting J, which should be a minus J. Sorry about that. Those should be minus J. So you get minus J times small divided by R. Okay. And so that gives you effectively a small number with an angle of minus 90 degrees. Okay. So these really should be negative signs here because they're capacitors. Okay. And so this small piece here falls away, and you just get R in the denominator, so you get a minus J, which is your minus 90 degree phase angle. So that would be for a low pass circuit. But for the high pass circuit, at high frequencies, okay, at high frequencies, for that you get for the high pass filter, this was R here. Okay, so you had R and then R minus J X of C, which X of C is small at high frequencies. And so when you're trying to answer these questions, okay, the word Bode plot is just talking about looking at all the different frequencies. Okay, so Bode plot is looking at high frequencies and low frequencies, but then over here I'm saying, well, hey, what happens at the high frequency? And so we're really just looking at this transfer function. Okay, you're looking at this voltage divider, right? A lot of times when we're talking about systems, they call this a transfer function. You're talking about how much of the input is transferred to the output. That's where the term transfer function comes from. But what it really is a voltage divider circuit. Okay, so it's just going and looking at the AC response, the voltage divider response of this circuit. How much is, what is the voltage out compared to the voltage in? Okay. So when you're doing all these Bode questions, you really need to just come back and think of this voltage divider circuit right here. Okay. So this is the voltage divider for the high pass. Okay. And if I copy that, okay, for the low pass, it's minus jx sub c. Okay. And so what happens is, you just need to evaluate it at given frequencies. Remember that x of c is equal to 1 over 2 times pi times the capacitance times the frequency. Okay. So the capacitance isn't changing. We've selected the capacitance. So now we're just looking at how does this change with frequency. And so we look at this and we say, well, at high frequency and low frequency, so at low frequency, x of c is really small. So this is small and this is small. And so we get a minus j close to 0 divided by some value of r. So we end up getting with a very small value, but it's got a negative angle for the low pass filter. Okay. So you just need to look at, you basically stick in some numbers. Okay. So what is a high frequency? Well, you first have to find the resonant frequency. So remember that FR is equal to 1 over 2 times pi times R times C. Okay, so you find out, well, what, given this plot, okay, all right, we'll see you later. I hope everything's okay, Josh. All right, so given this plot here, not this plot, but this circuit that we're looking at, we have R1 and C1. So we have 1 over 2 times pi times R times C. Okay, so R is 1,000 and C is 0.2 e to the minus 6, right, micro. And so if we plug that in, we get, I think I've got octave here somewhere. There it is. Okay. So we got 1 over 2 times pi times R, which was 1,000, times 0.02 e to the minus 6. Okay. And so that gives us our frequency here to be, 7.96 kilohertz. Okay. So that gives our frequency 7.96 kilohertz to our 3 significant digits. So this is our critical frequency here, or our cutoff frequency. Okay. All right, so if we wanted to plot the Bode plot of that, we need to find that frequency. Okay, so this is 100. Okay, so here is 100. Here is 1,000. Here is 10,000. Well, we need 8,000. So this is this right here is 1,000. So this value right here this value is 2,000, 3,000, 4,000, 5, 6, 7, 8. So right here at this value is 8,000. Okay. And so we want to go at 0 dB. Okay. So let's see, this is 3, 4, 5, 6, 7, 8. Okay. So what I'm going to do is I'm going to draw a little circle here to kind of mark this. Okay. And then we're going to draw a straight line. This is a high pass, so we're passing the high pass. It's supposed to be a line. Let me make that bigger. All right, so this is our critical frequency here. All right, and then at this frequency, every decade, when you go down a decade, so a decade, when this is a semi-log plot, right? So each one of these is a decade, okay? But we're going to the 8th one of that. So we're going down 20 dB per decade. So that's right here. Okay, and then you go down another decade and another 20 dB. Okay, and so see, this is your straight line Bode plot. Okay, the blue line is your straight line Bode plot for your for this high pass filter here. Okay, so that is the magnitude. Okay, so you have a magnitude of 0 dB, 0 decibels. Remember, we're doing voltage in, or voltage out divided by voltage in. Okay, so we're doing voltage out divided by voltage in. So at high frequencies, you're passing everything that's coming in. So if VN, let's say VN was 10 millivolts. Well, the thing is that you're passing all of VN. So V out is also going to be 10 millivolts because you're passing everything. Okay, so it doesn't matter what VN is, it's just you're passing everything. So you have, and that's, I was just typing in here, it wasn't a valid equation, so ignore the error. All right, and so you have V out divided by VN, which is 10 millivolts divided by 10 millivolts, right, which is 1. All right, now notice the millivolts cancel because it's millivolts divided by millivolts. The millivolts cancel, and so you have a gain of 1, which is the highest you can get without amplification. Okay, so this means that everything coming in is going to the output. Okay, it's a gain of 1. All right, so the highest you can have is a gain of 1 unless you add in an amplifier. And to add in an amplifier, you need something like a transistor or operational amplifier or something to amplify the input. I've mentioned before, this circuit has capacitors and resistors, and we could add an inductor in there. Those are passive devices, meaning they don't amplify anything, okay? They can only attenuate it, okay? So attenuation means it's going to end up being less than 1. So why, when I did the Bode plot then, why is it a 0? Well, that comes from its decibels. The units here are decibels, okay? And so remember that decibels, you can either calculate decibels in power or in voltage. Or actually, decibels are always power, okay? Decibels are always power. So let me get back here. I was just setting this up so I could do the thing. So let me get back to octave here, right? So remember that power in decibels, the equation for that is 10 times log power out divided by power in. Okay, but I haven't calculated any powers. Okay, but this is the equation for, again, ignore the errors because I'm just typing stuff in here which isn't valid commands. But the power is 10 times log. This is the definition of a decibel. Okay, this is, remember, the 10 comes from the fact that decibel. So remember, a bell was defined as being, log base 10, that's base 10 log, power out divided by power in, and decibels or decibels is 10 times that. That's where the number 10 comes from. Okay, I never remember this. I always have to look it up. I remember, why is it 10? I don't remember. Well, it's because it's deci. Okay, so the bell piece is just power out over power in, and then deci is 10 times that. However, we're dealing with voltages here, but decibels is defined as power. So what happens is, you remember that power, officially, power is voltage times current. But we know that current, I, using Ohm's law, is the voltage divided by the resistance. And so therefore, power is voltage times voltage divided by resistance. Okay? And so, assuming that the resistance for output and input is just 1, okay, to make life kind of simple, that's kind of an assumption that we're going to do. We have V times V, or V squared. Well, when you take the log base 10 of V squared, okay, the square, and this is the log function of it, the square comes out, and this gives you 2 times that. Okay, so this gives you 2 times the log of base 10 of voltage out divided by voltage in, because that's what we're looking at. All right, but that gives you a bell. This would be the bell. And then to do a decibel, we got to multiply times the 10. All right, so decibels, using voltages, decibels is 20 times the log of base 10 voltage out divided by voltage in. Okay, so if we say, now I can actually do this calculation here now. So I'm going to take 20 times log 10 divided by voltage out, which is 10 millivolts, okay, which 10 e to the minus 3 divided by the input, which I said was 10 e to the minus 3, right, which is just 1, gives me the decibel is simply 0. So when we look at this plot, it's 0 dBs up here, right? It's 0 dBs here, and that is what we're passing. So we're passing the 0 dB piece up here. This is what we're passing, and everything else here is being attenuated. Okay, this is being attenuated. And we get further away from that cutoff frequency, we have more attenuation. Okay. So that is the magnitude plot of a Bode plot. And I should have made a copy of this before I started drawing on it. But if we wanted to look at phase angles now, we need to go back and look at the phase angles. So we come back here to the circuit, and we were doing a high pass. The original question was the high pass filter. Okay, so at low frequencies, here, X of C is much, much bigger than R. Okay, at low frequencies. I should state that here. So at low frequencies, all right, the capacitor is acting like a short. All right, so then we end up getting R is small, okay, divided by something small, say it's close to 0, minus J X of C, which is really big. Okay, but now notice this is a minus down here. When you bring it to the top, it becomes a positive. All right, so this is going to give us something small, because we're not passing it, it's small, but we have an angle of plus 90 degrees. So there's this huge phase shift. Okay, so it's small with an angle of plus 90 degrees. Okay, 90 degrees. Okay, so when we, if we come over here and try to plot this here, try to make this as big as possible. All right, so we already had okay, so here's the original plot. What I'm going to do is I'm just going to copy this and paste it below here. And I don't know, it's kind of doesn't show real well on here, but so if we come over here, all right, and let me do this Bode plot here again. This is the magnitude up here. Okay, so we were right over here at the second one. Okay, so this was the magnitude. And then here, we're dropping off. Okay, so we're dropping off at minus 20. That's what I thought, it's way too small. Minus 20. Minus 20 dB per decade. Okay. So that's what this thing's doing here, is it's falling off at minus 20 dB per decade. All right, so, but now, if we look at the phase angle, okay, so let's go back and look at the phase angle. All right, so the high pass filter at low frequency here, we had a positive 90-degree angle. But at high frequency, okay, at high frequency, we end up having R over R, so the angle is 0. Okay. So what we need to do then is we need to draw that. We're going from plus 90 to 0 degrees. Okay. And so again, this is our critical this is our critical frequency here that we calculated. Okay. Not sure if those are perfectly lined up here, but that's our critical frequency. Well, when we're calculating the angles, we need to move over 1 decade. Okay, so we're going to move up 1 decade and down 1 decade to find that critical angle there. And so then we're going from, at low frequency, we're going at plus 90. And at high frequency, we're going to 0. So I got to change these values. Okay, so I'm just going to come over here and I'm just going to like cut this. Okay, so 0's down here. And so we have plus 90. And 0. This is our phase angle over here. And I'm going to go back and I'm going to draw a straight line. So I'm drawing a straight line up to this point here. I'm putting an extra layer of it just to make it show up. So there's a straight line there. Okay. Low frequency at an angle of plus 90. Okay, so it's plus 90 at low frequencies. And at high frequencies, which I don't have much of a plot here, way down here at high frequencies, it's there. Let me change colors. Maybe that'll help a little bit. Okay. And then you join these two together. Okay. And right here at this critical frequency, it didn't show up very well in this plot. Okay, but I should be at 45 degrees. Okay, so this here line is 45 degrees. And where it crosses here, if I would have let me draw it a little bit better, because I was up above here. I should, let's see, this is 90. Those are even. So yeah, so that should be 45 there. Okay, 45 degrees. Okay, and so when I draw this, I need to be right on this line. And when I draw this one, I need to be right on that line. I was a little high. Okay, it still seems a little bit off here. But right here, it should cross at 45 degrees. Okay, at that critical frequency. Okay. Looks like maybe my red line, this red line is actually off. The red line should be over here. It should be at this one here. It's hard to see at this zoom level. Okay, but this right here angle should be our 45-degree angle right here. All right, so that is, this is our Bode plot, okay? So this up here at the top is the magnitude. Okay, of the high pass filter. And this down here is the phase plot of the high pass filter. Okay, and so again, when you go and you're trying to answer these questions in Blackboard, okay, you really just need to go back and look at the transfer function. Okay, look at the transfer function and think about how this thing is changing here. Okay, so whether it's a high pass filter or if it's a low pass filter, this is your transfer function. But you need to look at that and just stick in frequencies and answer those questions. So I know Josh originally asked the question, but some of you others were saying that you were kind of having the same kind of questions. So as you go through these questions, that's what you need to do to answer these. Okay. And then for the very last question, question 18 here, the resonant frequency, remember that is defined as being 1 divided by 2 times pi times the square root of L times C for an RLC circuit. So that you just punch that in and get that. Okay. All right. So at resonant frequency, X of L and X of C cancel each other out. So the max current is the source voltage divided by R, because these two are effectively not there. Okay. And so it's just E divided by R gives you your maximum current. Okay. Maximum resistance voltage. Okay. Well, E, whatever E is. Okay. And then to calculate these voltages here, it's just do a voltage divider. Okay. To calculate VC and VL, you're just doing a voltage divider, just like what I was showing there. So that's what you need to do to be able to answer these questions. All right, so hopefully that'll help you guys with finishing up this homework.